Shh. I seem to have lost my monotone convergence theorem. So I'm going to move to the Lebesgue dominated convergence theorem. I think I wrote it and it didn't save. So let me, I'm just going to be only able to state the Lebesgue dominated convergence theorem and tell you what the monotone convergence theorem is. The monotone convergence theorem is actually a precursor to the Lebesgue dominated convergence theorem. And what it says essentially is that if I have a monotone increasing non-negative sequence of functions that converge to the measurable function f, that I can pull the limit inside from outside, that they're one and the same. And there's some conditions there. So I will state that for the next time that we meet. The Lebesgue dominated convergence theorem takes care of some of the constraints on the monotone convergence theorem, which requires non-negativity and monotone convergence of the sequence of functions. Here, as long as I have any sequence of functions that converges pointwise to f of x, then if I have another function which I know is integrable, and I know that it dominates f of x, that means that an absolute value, the magnitude of f of x, is less than or equal to g of x, and g of x is a non-negative function, then f is also known to be integrable, and the fn's are also integrable, and I can pull the limit in and out. And the Lebesgue dominated convergence theorem is the first thing that comes to mind when you're pulling limits in and out of an integral, because it is so versatile and flexible and easy to use, and it applies to a big class of functions, unlike the monotone convergence theorem. The Fatou's lemma, on the other hand, you don't have equality, so that's the bad part about Fatou's lemma. However, Fatou's lemma is also very versatile because it applies to a large class of functions. So without stating formally the monotone convergence theorem, I'll tell you that it's actually a theorem that has a lot of restrictions on it, but it's the beginning of a series of integration theorems that you can use to prove other results, or to use it in terms of partial differential equations, where we often have the sequence of functions converging to another function. The sequence of functions that we have converging have nice properties, and we'd like to extend that nice properties to its limit, which we're actually interested in. So I hope that I'll get time in the last day of class. We only have one more day of class, I believe, after this, to show you where all that plays in terms of functions that are important to us for partial differential equations.